Okay, so this is Chapter 7, Lesson 1, and we are going to start to talk about atomic structure. As I mentioned in class, there is not a lot of math in this unit, with the exception of the frequency and wavelength formulas, which if you're taking physics right now, you may have done that already. If not, when you get to it, it'll be easy peasy. So let's get started. So we're going to start to talk about the dual nature of light. Much of what we know about electronic structure, meaning the arrangement and energies of electrons around the nucleus, came from studying the light that atoms both absorb and release. Light behaves as both a wave and a particle, and when we refer to it as a particle, we refer to it as photons, or packets of energy. Even electrons and other solid particles can exhibit wave-like properties. Much of our experience with light has been light as visible light, but visible light is only one type of electromagnetic radiation, and there are many, many types of electromagnetic radiation, or radiant energy. There's X-rays, infrared, gamma, a whole bunch. They transmit energy in a wave-like behavior, much as waves in the ocean do. So there's a couple properties of waves that we need to learn about before we can get started. One is wavelength. That is the distance between two adjacent peaks or troughs. So if this is a wave, then this distance here is my wavelength. From the top of one peak to the top of another. The other is frequency, the number of complete wavelengths that pass a given point in 1 second. So imagine you're sitting at the end of a dock at the lake and you throw a rock in the lake and it causes some ripples. The number of ripples that pass where you're sitting at the end of that dock in 1 second is the frequency of that wave. All radiation moves at the speed of light. So these two variables can be related to the speed of light, which is defined as c equals lambda nu. And this did not copy the way it should have. So lambda nu. So this is wavelength and frequency. Now the physicists use a different symbol, I believe, for frequency. They may use an actual F. So I don't know why they can't get on board. And that is cycles per second, meaning hertz, Hz, or seconds to the -1. And then you have the speed of light, c, which is 3 times 10, and this should be to the 8th meters per second. And I believe it's fine on the PowerPoint. Just when it copied over into this program that I use, it changed some of the symbols. Okay, let's continue on. So here you see the electromagnetic spectrum, which consists of all different types of ER. We have radio waves, microwaves, infrared waves, visible, ultraviolet, X-ray, and gamma. One of the things that you should notice is that as frequency increases over here on the right, so frequency is increasing, wavelength is decreasing. And there's some examples here, which is like kind of nice. So radio waves are about the size of buildings. okay? That type of thing where gamma rays are about the size of atomic nuclei, and they give you frequency and then temperature of bodies emitting the wavelength. This picture shows you the difference between different types of frequency waves when pressure is constant, and it also shows you how those waves and frequency match up with the visible light spectra. So probably the biggest obstacle in doing the math in this unit is making sure that you can navigate between units of meters and nanometers or meters and picometers. So let's get that out of the way first. Please recall that 1 nanometer is equal to 10 to the minus 9 meters, and 1 picometer is equal to 10 to the minus 12 meters. So I would make sure that you have that handy. A laser is used in eye surgery to fuse detached retinas and produces radiation with a frequency of 4.69 times 10 to the 14th seconds to the minus 1. What is the wavelength of this radiation? And I believe in your PowerPoint it says negative 14. It is not negative 14. That's a typo, so make sure it says to the 14th. So, using our formula, C equals lambda nu. If we are solving for the wavelength, that means that wavelength is going to be C divided by nu. Our speed of light is 3.0 times 10 to the 8th meters per second, and our frequency is 4.69 times 10 to the 14th seconds to the minus 1. So when we solve, we get 6.4 times 10 to the negative 7th meters. Although much of our experience with light is as a wave, the wave-like properties of light could not be used to explain several other phenomena. And those included blackbody radiation, the photoelectric effect, and emission spectra of elements. But through the work of Louis de Broglie, we made some headway. So here we see light as both wave-like and particle-like. So when you have a light bulb, and light is emitted from the source, it causes electrons to be ejected from bulk material. And that would be particle behavior or particulate behavior, and then that same light, when passed through a prism, causes the light to be dispersed, which is our wave-like behavior. Here's just another picture of that. The difference between particulate, the electrons being ejected from the material, and wave-like, it being diffracted. And that's again through a prism. So along came Max Planck, who worked with blackbody radiation, and he found out when objects are heated, they give off radiation. And this radiation is related to temperature. So this creates a difference between red hot versus white hot. And the different color and intensity of radiation is dependent on the temperature. So classical physics could not explain this relationship between temperature and the color of the emitted light. However, Max Planck was able to explain this phenomena by assuming that energy can be released in discrete packets, called quanta. Quanta is the minimum energy absorbed or emitted whose energy is related to a frequency. He came up with the formula E equals h nu, where h is Planck's constant, 6.626 times 10 to the negative 34th joules per second. Nu is our frequency, and E is the energy value. As the frequency of radiation increases, the energy of that radiation increases by the increment h. So only certain energies are allowed. All energy must be a multiple of Planck's constant. So in that regard, energy is not quantized, it only exists in distinct quantities. So it is not continuous. Here's an easy way to understand the difference. On a ramp, each increment of energy brings progress. On a staircase, a minimum amount of energy is required to move up each step. So what have we learned so far? Light energy may behave as waves or as small particles, meaning photons. Particles may also behave as waves or small particles. And both matter and energy, light, only occur in discrete units, quantized. So here on the left you can see quantized, can stand only on steps. Here there's supposed to be a ramp. Which is non-quantized. This supports how electrons move from the ground state to the excited state. Some other examples of things that are quantized besides stair steps could be a typewriter, a light switch, turning it on and off, energy, matter, a piano even. Some examples of things that would be non-quantized are a violin or guitar, long jump distance, exchange rates, or a dimmer switch on a light. So a laser emits light with a frequency of 4.69 times 10 to the 14th seconds to the minus 1. What is the energy of one quantum of this energy? So we know that E equals h nu. And we know that E is equal to 6.626 times 10 to the negative 34th joules per second. And we multiply that by the frequency, which is 4.69 times 10 to the 14th seconds to the minus 1. That's going to give us an energy value equal to 3.11 times 10 to the negative 19 joules, because our seconds are going to cancel. That is the energy of one quantum. Now it says the laser emits an energy in pulses of short duration. If the laser emits 1.3 times 10 to the negative 2 joules of energy during a pulse, how many quanta of energy are emitted during the pulse? So we can take this energy emitted during a pulse and we can take the energy of one quantum, which we just determined to be 3.11 times 10 to the negative 19th joules. And we will get 4.2 times 10 to the 16th quanta. Or packets of energy. So that's how Max Planck worked through the blackbody radiation. Then along came Albert Einstein and the photoelectric effect. When light with a certain amount of energy is shown on a surface, it can cause the surface to emit electrons. Different materials require different frequencies of light in order to observe that effect. Einstein built upon the idea of light as a particle to explain this phenomenon, and he used Planck's constant and his equation to assume that the energy of a photon is equal to h nu. So, just to recap, photoelectric effect is when discrete particles of light called photons strike the surface and transfer all of their energy to the electrons on the surface of the metal. With enough energy, these electrons can overcome the attractive forces that hold them to the surface and bounce off the metal. That can generate a measurable voltage, which can be used to generate electricity. And on the next page is a model of this. So here you can see you have radiant energy that strikes the metal surface, causing the electrons to get energy. Once they have enough of that energy, there's like a certain threshold that they need to overcome their attractive forces. They can then change that into a measurable voltage. So de Broglie studied particles, meaning photons, electrons, and matter. And what he found out is that they will behave like particles and like waves, depending on the circumstances that they're in and what we're trying to observe. So lambda equals h divided by mv, where m is the mass, v is the velocity, h is Planck's constant. So this is different from nu. Nu has like a curve to it, which is frequency. So I wanted to make sure that you understood the difference between the two symbols. So an example is a 0.1 kilogram fastball traveling at 20 meters per second will have a wavelength of 3 times 10 to the negative 22nd picometers. Well, how can we figure this out? Well, wavelength equals h. So up here, we've got 6.626 times 10 to the negative 34th joules per second, divided by the mass, which is 0.1 kilograms, times 20 meters per second. And also, I should mention that 1 joule, you learn this in physics, is equal to 1 kilogram dot meters squared per second squared. So when I do the math on this, I'm going to come out with meters. I'm going to come out with 3.34 times 10 to the negative 34th meters. And to get it into picometers, I'm going to divide by 10 to the minus 12. And I'll get 3 times 10 to the negative 22nd. Another example is a 9 times 10 to the minus 31 kilogram electron traveling at 1 times 10 to the 5th meters per second will have a wavelength of 7,000 picometers. So I'm going to do the same thing, same equation. I'm going to wind up getting 7.4 times 10 to the minus 9th meters, and then do my dimensional analysis. 10 to the minus 12 meters is 1 picometer. and I actually get 7,362 picometers. They rounded it here in the PowerPoint. I think this one actually came out, yeah, they had 3, I came out with 3.34. Also working at the time was Niels Bohr, who was trying to explain the emission spectra. The emission spectra is caused by electrons with enough energy, quantized energy, moving from one energy level to another. A source of radiation often emits radiation that can be broken down into a continuous spectra, just like visible light through a prism will form a continuous rainbow. However, certain elements would not produce this continuous spectrum. Only light of certain wavelengths would be present, which would produce a line spectrum. And I've said this before, each element has its own specific line spectrum, very much like this, we have our own fingerprint. Okay, the first spectra to be studied was that of hydrogen. With only one electron, the spectrum was relatively simple. It only had 4 lines that were visible. One at 410 nanometers, one at 434, one at 486, and one at 656. Johann Balmer was able to write an equation that would allow us to calculate the wavelengths of all the spectral lines of hydrogen. And this is his equation that you see here, where 1 over lambda equals RH times 1 over n1 squared minus n2 squared, where n2 is greater than n1, and where n is equal to the principal energy level. RH is a constant, which is listed here. And oddly enough, he was a Swiss school teacher in 1885. So you can see there's a lot of people that had their hand in the mix back then. So now Niels Bohr comes along and he uses this to explain hydrogen's emission spectra, relating the different wavelengths being produced to the energy transitions between the principal energy levels. He proposed that electrons travel in circular orbits around the nucleus, and each orbit has a quantized energy state. When the electrons change state, the energy that is either gained or emitted is equal to the energy difference between the states. So we know that energy is emitted when we go from high to low, and that energy is absorbed when we go from low to high. With this, he was able to manipulate Rydberg's equation to calculate the energy for electrons in each orbit. And he did this by saying delta E is equal to negative RH 1 over, this really got messed up, okay, it's supposed to be NF squared minus 1 over NI squared. And yours has the initial first and the final second, and that is a typo. It should be the principal energy level final squared minus the principal energy level initial squared. So Rydberg's constant is redefined in this equation as negative RHHC. So RH is equal to 2.18 times 10 to the negative 18th joules, and N is the principal quantum number. All right, so let's do a practice. Calculate the wavelength of hydrogen emission line that corresponds to the transition of the electron from n equals 3 to n equals 1. So 3 is the initial state and 1 is the final state. So using our formula, we have delta E equals negative 2.18 times 10 to the negative 18th joules times 1 over 1 squared minus 1 over 3 squared. And when we do the math on this, we are going to get a negative 1.94 times 10 to the negative 18th joules. Now, you might see here that the answer is positive. Well, first of all, let's talk about this. We're going from 3 to 1, so we know energy is released. Therefore, that energy should be negative. But the energy of a photon is equal to h nu, which is going to equal to negative delta E, which should then equal a positive 1.94 times 10 to the negative 18th joules for the change. To solve for the frequency, recall that we have a formula, E equals h nu. So if we're solving for our frequency, then frequency is going to equal E divided by h. In this case, 1.94 times 10 to the negative 18th joules divided by 6.626 times 10 to the negative 34. Joules per second. And our joules are going to cancel, and we are going to get 2.92 times 10 to the 15th seconds to the minus 1. And in the last one, in solving for the wavelength, we know that lambda is equal to c over speed of light over nu. Therefore, the speed of light is equal to 3 times 10 to the 8th meters per second. We just solved for our frequency, which was 2.92 times 10 to the 15th seconds to the minus 1. And we're going to be left with a wavelength in meters of 1.03 times 10 to the negative 7th meters. Now this corresponds, if we look back on page 2 to the electromagnetic spectrum, this corresponds to the ultraviolet wavelength. Now usually wavelength is reported in nanometers, so just to get this to nanometers we would divide by 10 to the minus 9 meters, and this could also be reported as 103 nanometers. Okay, I believe that is it.